All right, let's get right into it. We all spend so much time wrangling data in NumPy, cleaning it, transforming it, doing all this complex work. But then what? How do you actually save it so you don't lose everything? You know, data persistence is one of those unsung heroes of any project. Get it right, and everything's smooth. Get it wrong, and it's a total nightmare. So today, we're going to master how to save and load NumPy arrays like a pro, taking those huge gigabyte-sized headaches and shrinking them down to fast, manageable bytes.
And to really get why this is so critical, let's start with a real-world story. This comes from the Primavera project. They built this amazing sensor system called Betsy to keep an eye on industrial bearings. The problem was they were collecting an absolute flood of data, and their first attempts to just store it all were, well, they were hitting a serious wall.
And when I say a flood, I'm not kidding. In just one 8-day test, their system generated over 200 gigabytes of vibration data. Think about that for a second. 200 gigs. That is a colossal amount of information to try and manage. And that leads us to the big question. It's not just a question for them, it's a question for any of us working with data. How do you handle something that big without your storage costs going through the roof and your programs grinding to a halt? The whole secret, it turns out, is picking the right file format from the very beginning. And wow, this chart right here, it tells the whole story. For the exact same data, just look at the insane difference in file size. Your standard text files like CSV or TXT are absolutely massive. They completely dwarf a more optimized binary format like ZAR. We're not talking a little bit bigger here. We are talking orders of magnitude. This just goes to show that your choice of format can have a huge impact on everything from storage space to performance. So, here's our game plan. We've seen the problem. Next, we're going to jump straight into NumPy's own built-in binary formats, the ones designed for speed. Then we'll cover the universal option, plain old text files. After that, we'll put them head-to-head, cover some pro-level techniques, and wrap up with a practical workflow you can start using immediately. Okay, first up, NumPy's own native binary formats. Let's call this the high-performance path. These are custom-built from the ground up to work seamlessly with NumPy arrays. If your data is going to live mostly inside the Python ecosystem, these formats are almost always going to be your best bet for pure speed and perfect precision. The most fundamental tool in our kit is the .npy format. The best way to think about it is like a custom-molded, perfect-fit case for a single NumPy array. It's not just fast, it's what we call a high-fidelity format. It saves everything about your array exactly as it is. The shape, the data type, there are no rounding errors, zero loss of precision. What you save is exactly what you get back. And using it is just about as simple as it gets. It's basically a two-function trick. You've got your array, you call np.save, give it a file name and your array, and boom, it's on your disk. To get it back, you just use np.load with the same file name. That's it. The array you load is a perfect clone of the one you saved. Okay, that's great for one array, but let's be honest. In the real world, especially in data science, we almost never have just one array, right? You've usually got a bunch of related things, your training features, the corresponding labels, maybe some validation data. Trying to save all of those as separate .npy files would get super messy really fast. And that's where the .npz format comes to the rescue. It's such an elegant solution. The Z in .npz, it literally just stands for zip. At its core, it's just a simple zip archive that acts as a container, bundling a bunch of your .npy files together into one clean, portable file. Now, the way you use it is really clever and feels very natural in Python. With np.saves, you pass in your arrays as keyword arguments. See here? We're not just passing arrays, we're giving them names, like features equals A and labels equals B. Those keywords then become the keys to get your data back. When you load the .npz file, you get this cool object that works just like a dictionary. You can just ask for data.features, and you get your features array back. It keeps everything so incredibly organized. NumPy also gives you another option, np.savez_compressed. It does exactly what the name says. It works just like saves, but it compresses everything. So you're faced with a classic trade-off, speed versus size. The compressed version gives you a much smaller file, which is awesome if you need to email it or archive it for a long time. But that compression takes a little extra CPU time, so it's a bit slower to save and load. The choice is yours. All right, so we've seen just how fast and efficient NumPy's binary formats are, but they do kind of live in their own little Python world. What happens when you need to share your data with a colleague who uses R, or you just want to open up your numbers in Excel and take a look? Well, that's when we turn to the universal path working with text files. To save your array as a text file, the function you want is np.savetxt. Now there are two arguments here that are really important to pay attention to. First is the delimiter. That's just the character that goes between your numbers. A comma, like we have here, gives you a standard CSV file. But the second one, fmt, is a really big deal. This controls how your numbers are formatted. Here we're telling it to only save 2 decimal places. If you forget this, NumPy might save your numbers with 16 decimal places, and your file size will just explode for no good reason.
Now, for reading that data back in, NumPy gives you 2 main tools. First, you have np.loadtxt. Think of this as the fast, simple option. If your data is perfectly clean, all numbers, no missing values, it's fantastic. But, real-world data is rarely perfect. And for that, you'll want np.genFromText. It's a little bit slower, sure, but it is so much more powerful and flexible. And its absolute killer feature is how it handles missing data.
And this right here is why genFromText is such a lifesaver. If you try to use loadtxt on a file that has some blank spots where data should be, it'll just give up and crash your program. genFromText is smarter. It sees an empty field, says, I see what's happening here, and it automatically converts it into NumPy's special not a number value, np.nan. Your code doesn't crash, the structure is preserved, and you can then go deal with those missing values in your analysis. It's brilliant.
So we've got 2 very different approaches, right? We have the fast and precise binary path, and we have the universal human-readable text path. Now, let's put them side by side to make it super clear when you should choose one over the other.
This table really lays it all out. When it comes to speed, size, and precision, binary formats win, hands down. It's not even a fair fight. But on the flip side, text files are the undisputed champions of human readability and portability. You can open a CSV file in pretty much any software on the planet. So here's a great rule of thumb. If your data is going to stay within your Python workflow, stick to NPY or NPZ. If you need to share it with someone else or just look at it in a spreadsheet, a CSV is your friend.
Okay, you've got the fundamentals down solid. Now it's time to level up. We're going to dive into a few advanced techniques and, just as importantly, some of the common gotchas or pitfalls that can trip you up. Getting these right is what really separates the pros.
So here's a classic nightmare scenario. You have a 50 gigabyte data file, but your laptop only has 16 gigs of RAM. What do? You can't load it. Well, the magic solution is a technique called memory mapping. When you use np.load, you can add this little argument, mmap_mode. And what it does is genius. It doesn't actually load the file into your RAM. Instead, it creates a special array that just points to the data on your hard drive. You can slice it and work with it just like a normal array. But NumPy only pulls the tiny chunks you actually ask for off the disk. It's like having access to the whole file without having to pay the massive memory cost.
And you don't have to take my word for it. The official NumPy documentation says it perfectly. It is especially useful for pulling out small pieces from gigantic files. For anyone working with big data, this feature isn't just useful, it's an absolute game changer. It makes the impossible possible.
Lastly, let's cover 3 critical things you need to watch out for. First, and this one is the most important, security. An NPY file can potentially contain executable code through a process called pickling. So the golden rule is this: if you did not create the file yourself, or if you don't trust the source 100%, always use allow_pickle equals false when you load it. Seriously, just make it a habit. Second, savetxt has a big limitation. It only works for 1D and 2D arrays, which brings us to our third point, the workaround. If you have a 3D array, like an image, you have to first reshape it into a 2D matrix, save that, and then remember to reshape it back to its original 3D form when you load it. It's a bit of a hack, but it gets the job done.
All right, let's tie everything we've learned together now. I'm going to walk you through a super practical workflow that you can just steal and apply to your own projects to make them way more efficient and a lot easier to reproduce. Okay, check this out. This is a really powerful pattern. You start with your raw data. Then you do some sort of heavy computation. That takes a long time. Maybe you're training a model, normalizing a giant data set, whatever. Now here's the key. Instead of rerunning that slow step every single time you open your project, you save the results. You use np.savez to bundle up both your original raw data and your new processed results into one file. The next day, you just load that .npz and bam, everything is right there instantly. It saves an incredible amount of time and makes your entire analysis perfectly reproducible.
And so that brings us to the end, and I'll leave you with this question to chew on. You now have this entire toolkit at your disposal. You've got the high-speed .npz for your internal work, the robust genFromText for messy external files, and even the superpower of memory mapping for when things get huge.
So looking ahead to your next project, how are you going to design your data pipeline to be faster, more efficient, and more robust from the very start?